Let us calculate the electrical energy of an electrochemical cell. So, electrical energy calculation. Electrical energy of an electrochemical cell equal to EMF of the cell into the amount of electricity passing through the cell. Electrical energy of an electrochemical cell is represented in terms of change in free energy. Normally, for a reversible electrode, delta G decreases. So we can say delta G equal to or minus delta G. Since delta G, free energy, is decreases in a reversible cell, we can use the negative sign. So minus delta G equal to EMF of the cell E into amount of electricity. So amount of electricity equal to amount of electricity means the number of electron transfer occurs in the reaction into Faraday's constant. So amount of electricity will be equal to number of electron transferred into Faraday's constant. So here N into F. That means change in free energy delta G equal to minus NF E. And if we consider an equilibrium reaction, so if the reaction is in equilibrium, the change in free energy delta G will be equal to 0 and E will be also equal to 0. This is the condition in equilibrium state. So if we consider this reaction as a spontaneous reaction, then the conditions are delta G is less than 0 and in the case of E it will be greater than 0. For non-spontaneous processes this condition will be reversed. That is delta G greater than 0 and E will be less than 0. By substituting delta G equal to minus NFE in Gibbs-Helmholtz equation, we can calculate the change in enthalpy delta H and change in entropy delta S of a electrochemical cell. So let us calculate those values. Now we can calculate the enthalpy and the entropy of reversible electrodes. So enthalpy and entropy of reversible electrodes can be derived from Gibbs-Helmholtz equation. So Gibbs-Helmholtz equation is this: delta G equal to delta H plus T dou delta G divided by dou T at constant pressure. So let us number this as equation number 1. From the above equation, it is clear that delta G equal to minus NFE. Let us number this as equation number 2. So if we differentiate equation number 2 with respect to temperature, at constant pressure, we will get dou delta G divided by dou T at constant pressure will be equal to, here N is a constant for a particular electrochemical cell, F is a constant and the variable, only one variable is E. So N, we can take N and F outside, and dou dou E divided by dou T at constant pressure. Then equation number 1 will change like this. Delta G equal to delta H minus NF dou E divided by dou T at constant pressure. Okay. So equation number 1 changes to delta G equal to delta H minus NFT dou E divided by dou T at a constant pressure. And according to Maxwell's equation, 4 Maxwell's equations are there. One of the Maxwell equation corresponding to delta G, free energy change is delta G equal to delta H minus T delta S. So let us number this as equation number 4 and this as equation number 5. If we compare 4 and 5, the LHS terms are same. So we can write it as delta H minus T delta S equal to delta H minus NFT dou E divided by dou T at constant pressure. We can cancel these two delta H terms and the minus sign also cancel. T is also there on both sides. So we'll get delta S equal to NF dou E divided by dou T at constant pressure. So this is the equation for delta S of a reversible electrode. Now we can find out the value of enthalpy, change in enthalpy, by substituting this delta S value in Maxwell's equation. So that is, we can rearrange Maxwell's relation as delta H equal to delta G plus T delta S. If I bring this term into LHS side, we'll get delta H equal to delta G plus T delta S. So here if I substitute the delta S value, then I'll get delta G plus NF dou E divided by dou T at constant pressure. This is the value of delta H. Now we can represent the enthalpy in terms of EMF. Enthalpy in terms of EMF can be derived from this equation, delta G equal to delta H minus NFT dou E divided by dou T at the constant pressure, and the equation delta G equal to minus NFE. So if we substitute delta NFE value here in this equation, we'll get minus NFE equal to delta H minus NFT dou E divided by dou T. So if I bring NFT term in one side, I'll get delta H equal to NFT dou E divided by dou T at constant pressure minus NFE. I'm going to take the constant term out. So I'll get NF into T dou E divided by dou T at constant pressure minus E. So this is delta H. So this is for enthalpy. If I want to calculate the EMF, then I can rearrange this equation as I can bring this term here, delta H divided by NF equal to T dou E divided by dou T at constant pressure minus E. From this, E value equal to minus delta H divided by NF plus T dou E divided by dou T at constant pressure. So this is the EMF value. Now let us calculate the EMF of an equilibrium reaction and its relation with equilibrium constant. So EMF of an equilibrium reaction. So Consider a general equilibrium reaction AA plus BB reversibly gives CC plus DD. Let Q is the equilibrium quotient the Q value will be equal to effective concentration of C raised to C, that is activity of C raised to C into activity of D raised to D divided by activity of A raised to A into activity of B raised to B. And the decrease in Gibbs free energy delta G equal to delta G0 minus RT ln Q. Here delta G is the Gibbs free energy, delta G0 is the standard Gibbs free energy, R is gas constant, T is temperature and Q is equilibrium quotient. And let me number it equation number 1. We know delta G equal to minus NFE, or we can write it as minus delta G equal to NFE. This is equation number 2. There is another relation which relate standard Gibbs free energy with equilibrium constant K. And the equation is delta G0, standard Gibbs free energy, delta G0 equal to minus RT ln Q. And this relation is known as Van Hoff reaction. Van Hoff relation. Okay. So by substituting these two values in equation number 1, we'll get NFE equal to RT ln K minus RT ln Q. Instead of Q, we can write it as AC raised to C, AD raised to D divided by A raised to A into A B raised to B. If we divide all the term by NF, we'll get E equal to RT by NF ln K minus RT by NF ln AC raised to C to AD raised to D divided by A raised to A into A B raised to B. And this will be equal to E equal to RT by NF log, we can multiply 2.303 log K minus RT by NF. Instead of this term, we can use simple concentration terms also. So 2.303 log concentration of C raised to C into D raised to D divided by concentration of A raised to A into concentration of B raised to B. Actually, this value will be equal to 0.303 RT divided by F will be equal to 0.059. So we can rewrite this equation as E equal to 0.059 divided by N log K minus 0.059 divided by N log concentration of C raised to C into D raised to D divided by concentration of A raised to A into concentration of B raised to B. Well, EMF, final equation to calculate EMF of an equilibrium reaction. Now, let us find out the relation of standard EMF and equilibrium constant. So we know delta G equal to minus NFE, right? If you are calculating the standard free energy, this will be equal to minus delta G0 equal to minus NFE0. Okay. According to Van Hoff equation, delta G0 equal to minus RT ln K. So from these two equation 1 and 2, we can write it as minus NFE0 equal to minus RT ln K. So E0 will be equal to RT by NF ln K. So this is the relation of standard EMF and equilibrium constant K. And we can use another relation called Nernst equation to calculate the cell EMF. So consider the equilibrium reaction AA plus BB reversibly gives CC plus DD. So according to Nernst equation, the equation is this: delta G equal to delta G0 plus RT ln concentration of products divided by concentration of reactant. Okay, from our previous knowledge we know delta G is equal to minus NFE and delta G0 equal to minus NFE0 plus 2.303 RT log concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to D. So here we can write, if we divide the equation throughout by NF minus NF, we'll get E equal to E0 minus 2.303 RT divided by NF log concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to D. This is the Nernst equation to calculate the cell EMF, and we know this value is a constant and it is equal to E0 minus this is equal to 0.059 divided by N log concentration of C raised to C, concentration of D raised to D divided by concentration of A raised to A, concentration of B raised to B. Okay, this is the Nernst equation to calculate cell EMF.